When I started ophthalmology in 1983, we didn't put implants in at all, so there was no such thing as biometry. So it's been a steep learning curve for me. I'm going to talk a little bit about definition, normal ranges. I think it's important to know a bit about A scans and a bit about partial coherence interferometry, or the IOL master, and then a little bit about sources of error. So if you look at the dictionary, this is what it tells you. It's quite sort of stale and difficult to interpret, but essentially what we want to know is how we measure parts of the body, either by ultrasound or MRI, and in ophthalmology that includes the axial length and keratometry in order to calculate intraocular lens power. And this is still the commonest cause of lawsuits in the United Kingdom in ophthalmology. So someone like me is more likely to be sued for a poor outcome in ophthalmology, in cataract surgery, because of poor biometry than in anything else. So it's an important topic. So it is important that we know these key components. Measuring the axial length by A-scan ultrasound or optical biometry, measuring the corneal Ks, however you do that nowadays, there are different ways of doing that we'll talk about. Calculating the intraocular lens power using the latest formulae. These change all the time. In the old days, when we started putting implants in, I used to use a 21 diopter lens in everybody. There wasn't a formula, so it was dead easy. Nowadays, the formulae are changing all the time, and the reasons that they're changing we'll talk about. You also need to know a little bit about their current spectacle correction and the status of the non-operated eye. And it's quite common. I always go into the anesthetic room before I do each case in my theatre, and I always say to the patient, I confirm which eye we're doing, and I say, are you happy that we're going to leave your distance set, your vision set for distance, and you'll have glasses for reading? And quite often they say, I don't know what you're talking about. And it's really important that this conversation is had before the surgery starts, because planning the refractive error beforehand to match the other eye and to balance them is absolutely critical. Now, I'm sure you all know how ultrasound works. The machine sends a wave into the eye, which is reflected off the back of the eye, and as the various media are crossed by the wave, you get interference, and this is recorded on a chart. And this can be done in an A scanner by contact tonometry. The problem with this is that there's often pressure on the cornea, so you get an artificially shallow anterior chamber. So we prefer to use a non-contact or immersion technique, where using a water bath, the probe is kept off the surface of the cornea with a water-filled gap, and it's a much more accurate way of doing A-scan readings. The echoes that come back look like this, and they're produced by impedances at the interfaces of different media. So number one there is the aqueous lens interface. Number two, you can read it, the lens vitreous, and so on and so forth. This is a nice clear scan showing the different structures in the eye as the ultrasound bounces back and forward. And this is really important to know. The human eye is somewhere between 21 and 26 millimeters in 94% of patients, 23 being the average. Corneal Ks round about 41 to 46, again about 43, 43 and a half. Anterior chamber depth is about 3 millimeters, and the lens thickness is around about half a centimeter, 5 millimeters. And knowing those things in your head means that when you come to look at the biometry before you do the operation for each patient, if something's abnormal, it will flag up in your mind as something to check. So learning the normal measurements are quite important. Also, what's important is the velocity of sound through different media. Now, when I was a boy, I used to watch a lot of cowboy films, and I was always intrigued when the cowboy got off his horse and put his ear to the ground. And I didn't know what he was listening for, but of course he was listening for horses coming over the hill, and he could hear them sooner by listening to the ground than he could by listening through the air, because sound travels a lot faster through solid than it does through air. And the same applies to the eye. If you have a very dense cataract, the crystalline lens, which is clear, sound has a velocity of 1,641 meters a second, but if you get a very dense cataract, it can go up much higher than that. And so it is important to know that and to assess if you've got a really dense cataract and you're using A-scan biometry, you have to allow for that by adjusting the gates on the machine. Also, what's important, at the bottom you'll see silicon oil. If you have a silicon oil-filled eye, the velocity is much slower, and the machine will therefore think the eyeball is much longer because it's taking longer for the sound to get there and back, and you'll get artificial hypermetropia as your result. So really important to know these figures and take them into account. What we tend to do if we're not getting good readings is just turn the gain up on the machine, and what happens if you do that is you simply increase the width of the beam that's going to the back of the eye. And the problem with that is that if this is your normal beam here, you'll see it produces a reflection here, but as soon as you turn the gain up, the width of the beam is much wider, so you're going to get a much earlier retinal spike. So by turning the gain up, you can alter the accuracy of the machine. And a typical reading that's with the gain set too low is like this. You get very poor spikes at all the interfaces. A normal reading, a too high reading would look like this, and the hallmark here is this squaring off at the top of the wave. And if you see that, you don't know where those two lines meet, somewhere up at infinity probably, and you can't tell where the top is. So is the retina there or is it there? You just can't tell. So if the gain is too high, you can't get accurate readings. And the optimum settings, you get these nice clear spikes with a proper point. They're all around about the same level, and that's a good reading. Now, in the old days, we used this formula. This is the original Sanders, Retzlaff, and Kratz formula, the SRK. And what you did was the power of the lens you wanted, P, was an A constant, which we can talk about, minus 0.9 times the average of the Ks, minus 2.5 times the axial length. Now, you can see from that the axial length has an important part to play, and if you get that wrong, your error is automatically multiplied by 2.5 times. So measuring the axial length accurately is very important. And nowadays, it's less important because other things are taken into account, such as effective lens position estimation, AC depth. And so the modern formulae aren't quite so dependent on it. So here's an example of something that went wrong. This is in the days before we had IOL master biometry. Apparently a straightforward scan in a -12 myope using the SRK2 formula. Nobody should use the SRK2 formula anymore. It's too old-fashioned, it's too inaccurate and shouldn't be used. So SRK-KT is all right, Haigis, Hoffer, and of course the Hill RBF formula now is coming into its own. But this patient ended up +3 and was extremely unhappy. Not as unhappy as the surgeon, obviously, but quite an unhappy patient. And looking at the scan, it was quite obvious that there was a problem here. It's perhaps a little difficult to see on this projection, but the retinal peak was thought to be here, and the retinal cursor was placed at the sclera here. And so the eye was measured too short, the cursor placed at the sclera, not at the retina. The patient ended up hypermetropic and very unhappy. So poor alignment is one of the reasons for this. You can tell if you have poor alignment because the peaks are uneven heights. So you can see here, these are very different height peaks. That usually means the scan is cutting across the lens at different levels, and the reflection, therefore, is coming back at a different level. So look out for that on the A scan. How can you tell it's right? Well, these are all the things that look good in a good scan. 4 or 5 clear peaks, lens peaks are approximately equal heights. You get a good retinal return which rises sharply from the baseline, and the gates are where you expect them to be. So it's always good practice to measure both eyes, make sure the patient has a fixation target to look at, take a minimum of 5 readings, always review the scans and delete the ones that are way out. The eyes are usually within 0.3 millimeters of each other. If they're not, you've got to explain why. They may be, but you've got to be able to explain that, and any difference in axial length measurement. And then be able to comment on the reliability of the scans according to their shape. That's really important. If they don't tie up, do a B scan, and we'll talk a bit about that in my second talk in a moment. Maybe seek a second opinion or a second lot of measurements, and those are good things to do. Optical biometry has made all of this a bit easier, and the reason basically is that it's much more accurate because ultrasound is accurate to about 1/10 of a millimeter, whereas light with a much shorter wavelength is accurate to about 1/100 of a millimeter, so about 10 times as accurate. When we talk about errors, you can talk about random errors, which are perhaps different for each patient, systematic errors, which are reproducible, but reproducible inaccurately, always in the same direction, and we don't often find those, we don't pick them up, and blunders, which become obvious when you know what they are. But if you look at the spread of results with ultrasound compared with IOL master, they're much tighter. There's a much smaller range of error with the IOL master in measurement. In terms of the scan itself, what you're looking for is a good, what's called a signal-to-noise ratio. So how much above the baseline noise is the signal rising? And in this case, it's 9.3. and that's a very good scan. It's an obvious peak where the retina is. Here's a borderline scan where the signal-to-noise ratio is 1.7, and it looks pretty obvious, but once you're getting below 2, you want to start thinking about rescanning. And here, you can't really tell what's noise and what's retina. That's a really poor scan with a signal-to-noise ratio of 1.4. You really can't rely on that to get an accurate A-scan measurement. So above 2 is good. Less than 1.5, you've got to distrust it and start again, really. And the typical lens star, similar to the RL Master, the typical peaks that you see, you're now looking at the retinal pigment epithelium and the inner limiting membrane, so the readings are slightly different to ultrasound for that reason, but the peaks are usually pretty obvious, and the machine, as I said, much more accurate than the ultrasound machine. The curvature of the cornea, the K readings, again, much more accurate. In my day, we used to use the old Yarvol-Schiotz keratometer, which was lights that shone on the cornea, and you used to adjust how far apart they were until they met on the cornea. So user error was a common cause for problems. But this machine uses LEDs projected onto the cornea. The reflection of that is photographed, and then the separation between the lights is measured to give curvature. And the machine goes to a lookup table and actually converts that measurement into radius of curvature, millimeters, radius of curvature. Again, it's an important thing to use. Some of these machines have a thing called a T-cone, which is like a topographer. And it is important to do topography in certain selected cases. Here's an example of a 62-year-old who wanted to have a myopic correction, cataract operation, had a myopic correction. Keen golfer, didn't like wearing glasses, wanted multifocal implants, likely to need torics, and the lens star was used with its T-cone attachment, producing the typical picture. And what the machine also does is it flags up readings that it thinks are inaccurate. Now, it's very easy to just ignore that. You look at it and think, well, that's the reading, I'll use that in my calculation. But it's actually telling you there's something wrong here, or it thinks there is something wrong, so it's always worth checking. And indeed, when we looked at the topography map, this patient had form-fruste keratoconus and an ectasia, and would have done very badly with a multifocal lens. So it really is important to listen to what these machines are telling us. They are much more accurate, and they will suggest that things are not normal if they think that's the point. Which lens do you choose? Having done your A-scan, in the old days, a lot of my training consultants used to say, well, I always add half a diopter or a diopter, and I go on the negative side because you don't want to end up hypermetropic. That's really bad. Patients hate that. And they all had this fudge factor, as they called it. They would add their own amount of myopia to try and make the thing work out. And in fact, nowadays, we don't need to do that. The machines are so accurate that we can actually go for the nearest to zero that the machine gives us. Now, I always used to go nearest to zero on the minus side, and indeed, if the readings are evenly spread about plus, if it's, say, plus 0.1 and minus 0.1, I'll always go for the minus 0.1, because when you're myopic, something's in focus. When you're hypermetropic, nothing's in focus until you have your glasses on. So always aim for a little bit of myopia if that worries you. But we can now afford to choose the nearest to zero because these machines are so much more accurate. So you don't any longer need a fudge factor. Check that the scan is good, that you can rely on it, that it's got a good signal-to-noise ratio, that you're happy with it. But if you are, you can actually pick the lens that's nearest to zero. And in this case, we'd go for a 19.25. There's no such thing because they don't make quarter diopter strengths, most people. But you'd pick the lens that was nearest to zero. In this case, it would be plus 0.14, not minus 0.2. Actually, that's fairly evenly split. You could take your pick. But go for the nearest to zero. Nowadays is okay. In the UK, we have a WHO checklist, World Health Organization checklist that we have to go through. And one of the things that our hospital requires is that we write the number of the lens on the whiteboard in theatre so that we all know what it is. Now, I've stopped that happening in my hospital because it's dangerous, and the reason it's dangerous is because of translational error. If you can write the wrong thing down, you can write it down badly, you can read it wrongly, so we just go by the printed output. And to prove this point, this is a photograph of the whiteboard. I currently have a Spanish fellow, and she writes her ones like that, but I write my sevens like that. So do you put in a 31.5 or a 37.5? Quite different. So really important not to use handwritten notes in the operating theatre to make a judgment about the lens strength. Now, just as a final point for this talk, a practical experiment that you can all do when you get back to work is to get a 2-diopter vertical prism and hold it in front of one eye. And if you can fuse the disparity, if you can make the images single, then try the same thing with the prism upside down. And if you can still fuse them, then you're one of only 20% of human beings, because most people can't fuse more than 2 diopters of vertical prism successfully. So it's really important to know this, because when you give someone glasses after their surgery, you've got to remember Prentice's rule. I won't ask who remembers it, because I never do. But Prentice's rule basically says that if you look downwards through a lens, for every 1 centimetre of displacement, you get a diopter of induced vertical prism. Now that's important if you're using bifocals or multifocals, because it means that although most people can put up with 3 or 4 diopters difference between the eyes in terms of their focusing, if you're using bifocals, they can only put up with 1.5 diopters of difference between the eyes, and if you're using trifocals, only 1 diopter of difference between the eyes, because of Prentice's rule. So it's really important to remember that and to make sure that the eyes are as equal as they can be if the patient requires glasses afterwards. So in summary, this is a critical part of our modern surgery. It's really important to involve the patient in the discussion about where they want to be left. I do have a colleague who's myopic, and he likes to think that everybody likes to be myopic, so he tries to convince patients that being -2 is actually what everybody wants. And what I've found over the years is that I ask people what they want, if they can understand it, but most people like to be left emmetropic with glasses for reading, but it is important to know, and I have had patients who say, I want to read in bed at night without my glasses, I want to be -2. So it's really important to know what they want, and check each lens against the individual name and the printout in theatre to make sure you get the right one. Thank you very much.